Hello, I'm James Hunt from ICAS, and we provide software for embedded systems and for cloud systems for connecting the devices from the edge to the cloud. We've been involved in the automotive industry for more than 10 years now, or we've actually delivered systems to the automotive industry for more than 10 years. And we do this based on memory-safe technology. And I'm going to talk about a little bit about why that's important and how you can do this for your systems. So of course, the embedded market is growing rapidly, and we have more and more connected devices. That means the possibilities of causing cybersecurity problems or for them coming about is growing dramatically. So we need to take more and more care about making sure that these things, that our systems are robust and they're cyber secure. Also, these systems are becoming more and more dynamic. So we want to be able to change how these devices work in the field. And again, this is another area where cybersecurity is extremely important. Okay, so what we see that memory safety, the lack of memory safety causes about 70% of all cybersecurity problems in the market. This is found not just from one company, but we see it with iOS, with Android, with Microsoft products. Anywhere the systems are in the net and the software behind it is not memory safe, we see this problem. So what can go wrong? Well, you can have a buffer overflow. You can go reference an object of the wrong type. Anything that enables the system to read into memory that it shouldn't is a memory safety problem. So if you use numbers as pointers, if you reference objects that have been freed, these all can lead to problems where a number is used as a pointer and you can get access to any memory in the system. And of course, these many attacks use this kind of problem to get access to the system and to plant code that's can break and get data from the system or make it behave in ways it shouldn't. Now this has become so important that I've listed some references here from the US government and other organizations that see memory safety as an essential part of ensuring that systems are secure in the field. Here's a definition of memory safety from Wikipedia. Of course, it's not very precise. The state of being protected from various software bugs and security vulnerabilities. And they list a couple different languages here where it's either provided or not. But the whole point is, or the essence is, that a program should not be able to take a random scalar value and turn it into a pointer. Memory should be only referenceable from a valid pointer from the program. Otherwise, these sorts of attacks can be made. Of course, memory leaking is another problem that can cause cyber concerns just because a system can run out of memory faster than it should. The minimal definition of a memory leak was you had memory that's no longer reachable by the system. So you had no reference to some piece of memory. And if you keep losing references to memory, of course, your system can run out of memory very quickly, particularly in an embedded system where resources are limited. But actually, people tend to use a more maximum definition where memory that's no longer used by the program or needed by the program is still in the system. It's not clear what this has to do with leaking, but this is why people talk about memory leaks in Java, because yeah, you can hoard memory, but it's not really a leak. But that's so we distinguish between unintentional object retention or hoarding and actually dropping memory. So here's a diagram of things that are reachable, things that are free, and then you can have unreachable memory that you cannot collect anymore. This is very difficult to debug because you need to have special tools to find it, whereas hoarded memory is a lot easier. You can look at a memory dump, you can see, oh, here's a structure that's collecting objects forever. Okay, so one of the major techniques used for ensuring memory safety is garbage collection. I mean, there are some others, but this is the main one. And there are different kinds of garbage collectors. You can go for something as simple as reference counting. There are some garbage collectors for C and C++ called conservative garbage collectors. These have the problem that they have to assume that any pointer is a reference to the heap. So they have a tendency to hang on to memory that's not necessary. And the other problem with C++ in particular is, well, I could just take an integer, turn it into a pointer, and I can do whatever I want anyway. So garbage collection doesn't help much unless you have a language that's designed for it, a language that forbids certain kinds of operations, that have a solid memory model, either published or unpublished. The two main kinds of garbage collectors that are used are mark and sweep collectors. Actually, even conservative collectors tend to be of this sort. And these collectors only move memory at the end when they compact the memory. And then you have copying collectors that use various heaps and copy from one heap to the next until you get to maybe generational collectors that do this at the end. Okay, but IoT systems are real-time, right? So there's some additional things that you have to worry about that you wouldn't necessarily worry about in cloud systems. And basically, OT systems have requirements on reaction that systems, that say cloud systems don't have or desktop systems don't have. When I say real time, I don't mean live data. I mean something that happens within a certain time. This does not necessarily be real fast, but it's really consistent. If I have a deadline, my system needs to reach it at any time. So if I'm reading a sensor and this data comes up, I need to get that data in a certain amount of time. If I don't, it's lost. Or if I have a system that's trying to react to the world, it has to react to the input signals within a certain time to be effective. I mean, it doesn't help you to turn the car after you've gone past the curve, right? It just doesn't help. So deadlines always have to be met. Each deadline has a priority, so you can decide which deadlines to do first. Usually the shorter the deadline, the higher the priority you want to use. So this implies a certain real-time scheduling behind it. And programming can be done either event-driven or time-driven. Very often, real-time systems are time-driven. They have something that happens at a certain frequency. So if you look at some data, there's a utility of that data. And this utility changes over time. Go back to the sensor or the curve example. If you can use the data within a certain time, everything's okay. But if that time goes off, the utility of that data goes down. A good example is, arriving at school. If you're a little late, it's not so bad. But if you're very late, it's quite bad, right, for your kids. So for real-time systems, you define a deadline based on the utility of the data or when you have to respond. There's usually a little bit of buffer there, as you can see. But the idea is the system should always react within this time. And these are codified also in avionics standards. Avionics standards also deal now with memory safety. In particular, DO 332 defines memory safety as part of what needs to be taken care of in such a system. And in the guidance, they list various different ways of doing this, things like object pooling or stack allocation, scope allocation, and of course, garbage collection. And the amount of work that needs to be done is dependent on the technique that you use. So if you use something like object pooling, which is very common in MISRA systems, for instance, then you have to ensure that each one of the various objectives are fulfilled for each and every application. So it means application code. Whereas if I use an exact garbage collector, I can rely on the underlying garbage collector to do most of these things, and I only have to worry about how much memory is available to the system. The problem with garbage collection in real time is usually the garbage collector runs as a task. The task has to be scheduled. During the time that this garbage collection is running, other things need to be blocked, particularly if memory is being moved in the system. That's why in a real-time system, you want to use a different kind of collector. Here, a work-based collector works well because the actual garbage collection work is done at allocation time, so the programmer understands when it happens. But also, it can be done at the proper priority so that it doesn't disturb the reaction time of the system. So a high priority task that doesn't allocate any memory doesn't need to pay any garbage collection penalty whatsoever. Of course, there's other things that you have to worry about for real-time systems. You need some systems generally have some way of synchronizing between threads. And in order to do this, monitors are very often used. Unless you program your system properly, then you get a monitor where priority is ignored. I mean, there is a way to do this in POSIX, but you can get this situation where a high priority thread A wants to use a monitor that's being used by a low priority task C that's being blocked because some other task comes in the middle. And this can result in a deadline being missed. And therefore, it's important that all the monitors used in the system are priority aware. In other words, use something like priority inheritance, which is common on most POSIX systems, or some other inversion avoidance mechanism. Okay, so Java is memory safe, but conventional Java is not real time. So therefore, there's now a real-time and embedded specification for Java, which adds the features to Java and sort of extends the semantics of the language to cover these things that I've just discussed. So there's support for real-time programming, where you talk about importance versus fair scheduling. There are some things, anything that's time critical, you need to have a notion of importance of priority. You want deterministic response rather than, rather than, oh yes, if I'm typing on my keyboard, it should happen first, but it's not that important. So you have timeliness versus throughput. You also need things like device access. You don't want to run J&I code to access devices, because then you have the issue of memory safety again that you have to reevaluate, and you need to be able to interact with the environment. And there's some standard refinements, and this is a standard now of the Java community process. So real-time Java gives you Ada-like API semantics, where you can do not only the standard Java 10, 1 to 10 priorities, but also priorities above, which are reserved for real-time scheduling that are mapped then to a FIFO scheduler. You need to do event handling, and there's direct access to memory. All events, active events are handled the same way, so it doesn't matter if you're triggering off a timer or a happening, which is something from outside, or a POSIX signal. The way you program is completely the same. And of course, you have user-defined clocks and other facilities that make it easier to write in a runtime system. You can even control the CPU on which a particular thread runs. And sometimes you want to segregate your application to a real-time part that runs on some threads and other parts that don't, and this gives you the capability to do that. So, here's a sort of a try to get at, what languages support real-time memory-safe programming and what don't. So you have C and C++, which you can do real-time programming in, but of course you have to rely directly on the underlying operating system for that, particularly POSIX for your thread stuff. There is a memory model, but you don't have any kind of memory safety. So you need to do a lot more work in your application, your testing, et cetera, to ensure that you don't have memory safety problems in your code, and that can be quite expensive. You have other things like JavaScript and Python, which give you some things, but not really good for real-time programming. Also the standard VMs languages. Rust is an interesting new language. It has a lot of the things that you're looking for, but they don't yet have a real solid memory model, so that means if you move from one compiler to the other, your application could run differently. And it's still in flux, and the memory model is quite complex. You have this concept of ownership where you can cover a lot of things for local access, but as soon as you go into moving things between threads, then they also have a referencing counting as a backup for that. And the problem with referencing counting, of course, is that you can create a cycle that'll never be collected. And I think as Rust matures, it'll be interesting for certain kind of things, but it's not very dynamic. It's very difficult to add code to a running system that's run on Rust, whereas real-time Java gives you all these things as a simpler memory. It's a well-defined memory model. And as long as you don't go to JNI, you can build very, very robust programs. And like I said, we've had more than 10 years of experience of actually deploying this kind of software with a zero defect rate. Speaks a lot toward memory safety using real-time Java. Now, of course, you actually need more than that. Languages are nice, but if you want to do over-the-air update, then you need something that you can use to download code, run that code, etc. And there are various techniques, but one very good technique that we use is OSGi, because you have really very small services. The cost of adding a service is much smaller in an OSGi system than say, running a new container in your system. You have a service-oriented architecture, so you have all the things necessary for registry, et cetera, for running such a system. And of course, you can run things message-based as well. So there's data buses. And basically, if you're communicating through two services that are in the same address space, it's a lot faster than if you have to serialize and deserialize to send it over even a shared memory interface. Of course, OSGi itself is not real-time, but it can be extended. We've shown how that can be done. There's some small changes that need to be made to the basic system because in a real-time system you want to have things that are pre-compiled and not use a JIT, because a JIT adds both size to the VM, but also changes the performance of a call over time. So first slow, then really slow, and then very fast. And of course, for real time, this is not really acceptable because you can never warm up everything at each start. It just doesn't work very well. So we can pre-compile the bundle 0 into the framework, so that's always there. Then any other bundles that are downloaded, we can pre-compile those as well. They get linked as shared libraries into the system, so we can get the consistent performance even with downloaded code. Of course, you need to make sure that the management threads can always run, which means if you have a real-time piece of code in there, you have to make sure that no matter what happens, that code can't block the whole system. And if any of you have done real-time, who's done real-time programming? So you know what happens if you have an infinite loop with a high priority thread, right? System's dead. So if you have a framework and you download code, you want to make sure that even if that happens, the system doesn't lock up. Okay, so there's resource management to provide the real-time specification for Java provides mechanisms for limiting CPU in a part of the system. So under the process level, and it provides a way of limiting task memory use, but also we have a way of terminating bundles positively but safely by making sure that all the finalizer clauses are executed even if the thread is terminated. So if something really runs amok, you can end it safely. It gives essentially a process model at the bundle level. And therefore, it's very easy to manage then different things that are on the system. You can ask about, how much of the system is being used based on what the restrictions are in each bundle. And then even talk about, okay, is this system, are there too many bundles running or not? You can limit the numbers of bundles that are running to keep the system live at all times. Of course, these are independent of the Java security model. There are some other things that you want to use the Java security model for if you're trying to limit the disk use or the network use of a particular bundle. Okay. So this is just a comparison of some frameworks that are out there and where they're good and not good. And memory safety is something that the only framework out there that really provides memory safety is OSGi that I'm aware of, or at least it's widely used. There's even some guys that tried to build an OSGi-like system in C++, and that doesn't really work very well because you don't have the memory safety. So if you add an element to your system and it has an error, that error could manifest in any part of the system, whereas in a memory safety safe system, if there's an error in an application, you get a local exception that you can trace and see what the problem is, debug it relatively quickly. That's not the case in AutoSAR or some of the others. Containers, yes, you can get memory safety if you use Java in the container, but then you have the Java problem, the standard Java problem. And also, as I said before, containers are very, very heavyweight. They bring a lot of stuff with them. Communication between containers is much slower. So, for the systems that we develop, we use then OSGi, a real-time OSGi for it. So, as a quick summary, I think I would ask if there are any questions.
Hello, I have a question.
Hi.
You hear me?
Yes.
Okay. So you compared some languages from a real-time memory safety standpoint
Yes.
before. I wonder where Ada places in that comparison and what are its advantages and disadvantages when compared to Java real-time, for example.
Yeah. Like memory safety is still a bit of an issue so for the real-time applications, Ada has a lot of what you need. I mean, the real-time specification for Java, half the people who worked on it came from the Ada environment. So a lot of these advantages are covered. But the memory usage, is still kind of an open issue with most Ada implementations. So a lot of Ada developers use Ravenscar, where you're not allowed to allocate anything. Everything's allocated at the beginning, and then what you end up is doing memory pooling. I mean, that's what really happens. So you still have a certain burden in your application to make sure that objects aren't reused, etc. Because again, if you return something to pool and it's still in use, well, that's a deallocation, So,
Thank you.
you're welcome. Any other questions?
Do you see that the WebAssembly could address some issue? Because I see paper or presentation that of Bosch that showed that WebAssembly is good for real time, and now with a new component model where you can have isolated component, could be in the future, let's say, a solution for real time and guarantee the isolation and have a component that you can load and unload.
Yeah, I haven't seen everything that's in there, but you still have the communication problem. What kind of monitors does the system provide? You'd have to make sure that those use at least party inheritance protocol. And the other thing is, I don't know what facilities are available for setting priorities within the system that are above. So there's some things there that you need to do. But memory safety is not just between containers. This is a fallacy. It has to do with I have data coming from outside that I process, and what can happen with that data, or does that violate what happens in that container? And you can use a container to kind of limit the scope, but that doesn't solve the problem. You need a memory model that's complete enough that you can have an exact garbage collector, and I'm not sure that that's the case yet. I won't say it won't happen, but I don't think that's the case yet. Does that answer your question? Yes. Thanks. Anybody else? Well, then I thank you for your time, and I hope you enjoyed the talk.